Good morning, everybody. We are still in the land of phase transitions, what we started last week. Let me make a simple recap. What we have done and where we are going. So let's consider a system. We know, or we treated a lot of systems where everything was absolutely continuous. But from our everyday experience, we know that there are systems that the transitions are not continuous. And the simplest example is the liquid-gas transition, right? So I described to you, we can heat water, and some of the water will vaporize, and we will get a system where here we have water or liquid, and over here we will have gas, which are vapor. Right. Now, the following assumption holds. Let's assume that we prepare the system and part of the system is still sitting in the liquid phase and part of the system is still sitting in the, or is already sitting in the gaseous phase. Now, what do we know? And the systems now, I put adiabatic constraints and I keep the system in equilibrium. I apply pressure, I somehow set the temperature, etc., etc. So I have a coexistence of gas and liquid. Okay. One phase, another phase. We know that the transition somehow occurred abruptly. We watched the creation of the bubbles that came from the downside of our kettle. But now the system is in equilibrium. And now we want to somehow to understand what's actually going on. The things that we know from thermodynamics is, well, we only know that everything is continuous somehow, but we also know that the moment that the system is in equilibrium, it is some sort of stability conditions must hold, right? So what I mean by stability conditions, we had two stability conditions. First of all the generalized forces, are homogeneous. Namely, the pressure is the same everywhere inside the system. The temperature is the same everywhere inside the system. The chemical potential is the same everywhere inside the system. Okay? So those are stability condition number one. Conditions. Stability condition number two was that the derivatives of generalized forces with respect to their conjugated variables that are positive. So the derivative of the temperature with respect to the entropy is positive. The derivative of minus the pressure, because minus pressure is our generalized force, with respect to the volume is positive. The derivative of the chemical potential with respect to the number of particles is positive. Okay, so this is what we know, and this is what we want to apply on this system to inspect the phase transition. Now, we look on the system, we put it in equilibrium. The moment that we put it in equilibrium, those stability conditions apply. And first of all, we look, all the generalized forces are homogeneous. So it means that P in gas and P in liquid are exactly the same. It means that the temperature in gas and the temperature in liquid is exactly the same. It means that the chemical potential in gas and the chemical potential in liquid is exactly the same. So if you remember, I plotted this two-dimensional manifold which connected t, mu, and p. Said, well, they have to be continuous, but there could be some lines, coexistent lines, across which the transition of those intensive variables is continuous, but their derivatives don't have to be continuous. So this is why we use the Gibbs-Duhem equation. That's minus mu minus s dp minus, plus v dp. S, it is the total entropy divided by the number of particles, and v is the total volume divided by the number of particles. But using this equation, we understand that, first of all, why we use it, because the forces are exactly the same. We look on this and we want to use an equation which applies by T, mu, and P, because they are generalized forces and they are exactly the same in two phases of the matter. This is first of all. B, we understand from this equation that if a jump occurs, and we know that the general properties of a gas are very, very much different than the properties of a liquid, we know that there could be a jump. So the function itself transits continuously from liquid to gas. Mu here and mu here is the same. P here and P here are the same, the temperature is the same. But those guys can jump. So abrupt jump in entropy per molecule or in volume per molecule. So this is something that occurs during the phase transition. Specific bad properties that are intrinsic and are modified. Afterwards, we developed the Clausius-Clapeyron equation, okay, which specifically stated if you have P as a function of T, and there is a coexistent line which separates the two phases, we have phase A and we have phase B. Okay. The Clausius-Clapeyron states that dP and dt to dt, it is delta S divided by delta V. Okay. Okay, so this is something that happens during a phase transition. We know there is a jump in entropy per molecule, a jump in volume per molecule, and how exactly this coexistent line behaves depends on how much jump there was in the entropy and how much jump there was in the volume. And this coexistence line it exactly describes the situation where the two phases can coexist with each other. Okay. So the idea, use those guys. If you want to use only generalized forces because they are continuous, use Gibbs-Duhem. The moment that you have Gibbs-Duhem, you understand that the jump occurs in the intensive, extensive variables per molecule, and you can derive equations that describes exactly where the phase transition will occur. Great. Yes.
So, okay, when you have this coexistence state,
Yeah.
this is it represented by exactly one point on the graph, right? Because you have one.
For specific temperature and for specific mu and specific T. Yes.
But even from that one point, you can tell the jump because you just look at the derivative of the line at that point.
Yes.
Okay. So.
Yeah. There are situations where you have other phases. So, for example, we can have phase C, right? And you can have triple points and etc. etc. Depends on how many phases you have in matter. Great, but so this is where we got last week. This is the point that we stopped. Okay. But first of all, the problem is, well, I don't really know what delta S is, what delta V is. You'll see in the tutorial somehow that you provided those delta S and delta V. I want to understand a little bit more about what happens during the phase transitions. Okay? And so far, we have used only one principle from those two principles that I wrote on the board. So we've used stability number 1, but we haven't used stability number 2. Okay? We haven't used stability number 2. Now, what stability number 2 tells us, together with those jumps that we know that are occurring in S and V and etc., they tell us the following things. First of all, if you look on the volume as the function of pressure, right? So pressure usually it's something that I can control. Okay? So maybe it's a good idea to look on the volume as a function of pressure. So if I have a system and I'm looking on my volume as a function of my pressure, what will happen is, so for example, it will go somehow down. The existence of a phase transition and an abrupt jump in the entropy or the volume tells us that, okay, so we started over here, we increased the volume, the pressure, the volume got down. At some point, okay, we are still trying to extend the pressure a little bit, okay, and the volume jumps. Okay, so we have V alpha and we'll get V beta, okay? So we have indefinitely crossed a specific threshold, okay, of the pressure, and there was an abrupt jump in the volume. So this is how phase transition will look like. You increase your pressure, you measure the volume, you increase the volume gets down as it, you press more and more and more. At some point, there is a huge jump. Okay, so you can say this is our phase A, and here we have phase B, and this is how the transition occurs. But you see, to study such plots, it's not such a good idea. Why it's not such a good idea? Oh, it is, but let's study something else. The stability criteria tells us, well, we don't look on P as a function of V. I'm sorry, V as a function of V. We have this dP by dV with a minus is larger than 0, right? Let's put the minus inside. Minus. So this is the second criterion of stability. So we know that dP to dV is smaller than 0. Always. In order for a system to be in some stable situation, we have to always observe dP to dV smaller than 0. Okay. Great. So this is already some sort of a criteria that we can use in order to find phase transitions. So there is one thing, and this is the Clausius-Clapeyron and the coexistence line, one thing to go and measure it, right? I can have a lab, and in my lab I can heat up things, I can extend pressure, etc., etc. But what if I want to understand nature by trying to writing models and exploring these models? Okay. So I can write a model, I can check it whether it works in a specific set of parameters, okay? And then I say, well, what happens to the model if I'll do this and that to some specific variables, right? Then I'll have a prediction about what happens inside the system. This is a prediction. So I can say, well, let's write a model, describe a certain types of systems, and explore it. And if this criteria won't work, I will know that I will have some sort of a phase transition. Okay? So if I will see specific abrupt changes or something like that, I will understand, oh, a phase transition occurs over here. Okay? So this is why I'm doing all that. Otherwise, I could stay with the Clausius Paperon. Somebody will measure something, okay? Provide to me the values of delta S and delta V. But no, we want to go into modeling in order to describe our nature. Why? Because it's not always possible to measure everything. Usually, the research goes, somebody measures something, I get a qualitative understanding, I quantitatively describe it by writing some equations, I extend the applicability of those equations to areas where nothing was measured before, I make predictions, and I go and measure it again to see whether I'm right or wrong. Okay? And usually this is how discoveries happen. Okay, so we need simple models in order to describe and see whether we can use these criteria and stability criteria to see phase transitions. Okay, so let's talk about gases. What is the simplest model that you see that describe gases? Ideal gas, right? Ideal gas will be the first model. We'll only have two. Okay, so what ideal gas tells us? The ideal gas, the equation that you derived in thermodynamics, or in some other class, it is the pressure that you have multiplied by the volume equals to the number of molecules that you have inside your system, K Boltzmann multiplied by T. Okay, so in this unit, T is as the absolute temperature, K Boltzmann, you know what it is, N is the number of molecules. Sometimes you see this expression that's written in moles and etc., but we won't worry about moles and those chemical language. Number of molecules, specific constant that we call a Boltzmann constant, temperature, volume, pressure. Okay? Great. So this is the equation. This is a prediction. Okay? Let's see what happens for this equation. So in order to see whether there is a phase transition in ideal gas, we need to look whether their dP to dV is always smaller than 0. If it's always smaller than 0, it's always in one phase. This is P, this is V. Okay? P as a function of V is N K Boltzmann temperature divided by volume. Is something interesting happens to this model?
Yes, V equals 0.
Can V equal be 0?
No.
Well, exactly. It's so you're right. In general, when we plot those guys, let's plot different isotherms. So I pick up a specific temperature, the number of molecules stays exactly the same, K Boltzmann is the same, and I vary the volume of this guy. So right, when I approach, volume goes to 0, there is some sort of divergency, but I don't really, well, not experimentally, I cannot really reach this limit when the volume goes to 0. So for different isotherms, let's go with T1, and we have T2, and we can have T3. Nothing interesting happens. Why? Because dP to dV equals to minus nk Boltzmann T divided by V squared. N is positive, K Boltzmann positive, temperature is positive. We are working in the limit where there is an absolute 0 minus 27.3 Kelvin. We're working with kelvins. Okay, so this is positive. Our volume has to be positive, and it's volume squared, so we don't really care if it's positive or not. So this is always negative. The stability criteria is always satisfied. Nothing funky happens. Okay, so this is a nice model that derived already in high school. So if you studied thermodynamics in high school and then derived in thermodynamics, but this is boring, absolutely boring, and nothing happens over here. Okay, now this is the usual case for phase transitions, because if you have been taught what is the idea behind the ideal gas, the idea is that you have molecules that do not interact with each other. They transfer momentum to the walls, and back to the system, to the walls and back to the system. There are absolutely no collisions between the different molecules inside the gas. Okay? No interactions, nothing happens. Okay? So if you think about it, so the transition from liquid to gas, you see that the system solidifies, right? So you cannot press on it and it will splash around. So something in the interactions inside the material, this is what brings us the phase transition. This is what brings us the different aspects of matter. When nothing happens, you can heat it up. While you heat the system up, what happens? It will have more kinetic energy, but this kinetic energy doesn't come to the interactions. There are absolutely no collisions between the different particles. Absolutely nothing happens. Boring equation, boring outcome. What can we do? Now, they already knew when they developed this equation that it's not true. It describes very well very dilute gases. Extremely well. But the gases have to be very, very dilute. They've seen that something different happens when the gases became less dilute. There was more pressure. There was a transition from gas to liquid. Everybody knew that. And this ideal gas equation was absolutely not correct. Okay, so what do we have to do in order to modify this equation in order to see something interesting? And the first guy who did it had the name van der Waals. So he understood something about interactions between molecules or inside the gases. He developed van der Waals equation. Okay. Now, there's something very nice about how he developed this equation, because it's simple hand-waving arguments. We will do them. But the outcome is extremely, well, I won't say popular, but it's extremely useful. The van der Waals equation that we will obtain, it's simple enough, but it describes huge number of gases and it predicts something else. Okay, so what van der Waals thought to himself? He started, well, I have this PV equals to n K Boltzmann T. It wasn't about K Boltzmann, there is some other constant, but we'll speak in our language, not in the language of van der Waals. Okay, so first of all, as you said, well, something happens when the volume goes to zero. But can the volume actually go to zero?
No, you have to like,
There is a minimum volume of the molecules, right?
eventually they start interacting.
Or forget about interactions, even if you don't have interactions. So I compress those things, okay? Now there is a molecule. Well, we know right now that there is atom. Now you cannot compress the atom at all, okay? So eventually, okay, there is a given volume that cannot be used. So he said, well, this V over here that we are using, okay, it is what? It is V free. The only thing that you apply your whatever you're doing to the system is to the free volume. Okay? What is the free volume? Free volume is the volume of the system, V, minus number of particles
Times volume of each.
let's call it B. B is a positive constant that is describing the self-volume of each particle. Okay?
Can we assume that the size of each particle is the same?
So homogeneous gases. So you're right, if we have different particles, it's going to be a little bit different. But on average, B will describe the average size of the molecule. Okay? Now, those are wonderful ideas from van der Waals, because it's 19th century. The idea that everything is composed out of atoms is still not proven. Okay? It's just an idea that's floating around. And there is a lot of speculations where the matter is continuous or it's not granular, but atomistic. Okay, so very nice thinking. So this is V free. Okay, now as something happens to the pressure. So this is good. This is, we need to put inside, plug inside this equation instead of volume. Okay, we apply something to the system, and what is changing is the free volume. Okay, and we have to apply instead of V over here, Okay, we have to use V free. The second idea of van der Waals was the following. There is pressure. The pressure that you observe inside the system. Okay. Now what is the pressure? The pressure, you have particles. Think about ideal gas. You have particles and the particles are hitting the wall from time to time. The pressure that you measure, okay, comes from the impact of those single particles on the walls of the chamber, right? Okay. But if there is attraction, so we said, well, there are molecules, but if there are attractions between different particles, so the particle that tries to hit the wall of the chamber, it's actually attracted backwards a little bit by the neighbors, okay? So it tries to hit, but the impulse is a little bit smaller due to the attraction, okay? So the pressure that we observe is the P ideal, okay? As if there was absolutely no attractions, minus the attraction. So there is some pressure that gets down. Why it get down? Okay? Due to the attraction between the different particles. Okay? So the pressure that we put inside over here that comes due to the interactions and impulses, the ideal equals to P plus P attraction. Okay. Now, here we plug inside and multiply it by V. Okay, because, well, there are some specific number of particles, and each particle stays in volume V, etc., etc. Here, we need to reason what P attraction is. Okay. And what is P attraction? So first of all, how many molecules? So the attraction comes from the different molecules around each guy, around each molecule that it actually interacts with. Okay? So the potential energy or the energy that the system interacts with, or not the system, the single guy sees around it, it is minus N divided by V multiplied by some A. Okay. So N divided by V is the average particle number per volume around each guy. The average, it's a hand-waving argument. Maybe there is more on this side, maybe there is less on that side, maybe there's more on the other part of the chamber, but each particle, okay, look around it, and, oh, I have all those neighbors. And those neighbors attract me somehow. And this attraction reduces the pressure. Okay? How many neighbors on average I have? I take the top total number of particles and they divide it by the total volume of the system. Okay? Now, why there is a minus over here? Because it actually lowers the energy. So if I have attraction between those two guys, the energy gets lower. Okay? Now A over here is some constant that is greater than 0. Yes?
Shouldn't this happen only at the boundary?
No, so it happens everywhere.
But usually this happens only because the particles are only on one side at the boundary. When they're all
So
around.
each particle, it happens to it somehow, and we say that whenever happens, and this pressure is homogeneous inside the whole system.
Yeah, but if it's homogeneous around the particle, shouldn't it cancel itself out?
No. If it cancels, there is no forces. The pressure is the pressure from here, and there is pressure over there. It's like a tension, right? It's like a tension. So if I have of this, I'm pulling it, okay? The forces cancel, but the tension is not. Okay? The pressure eventually, this is why I'm using pressure. Pressure won't cancel. Forces will cancel, but the pressure is something different.
But what about force? What about taking the force that's created from this potential? Where you do a gradient of this and you get.
It's a first order approximation. Okay? You say that there I have something else. Well, maybe, yeah.
Oh, it's just a constant, so gradient there is.
Yes. It's just a first order contribution. Okay. Okay. Now, so this is per molecule. Write it down. This is the additional energy that eventually defines P attraction per molecule. What is the total energy that gets added to the system or subtracted to the system due to all these interactions? The first order approximation. So U total, it is what? It is N multiplied by U molecule, right? Which equals to minus N squared divided by VA. Okay. What is du total to dv with a minus sign? Why use this equation at all? Why use this derivative at all? Remember, dE equals TdS minus PdV plus mu dN. Right? This is an equation that you have to have in your mind all the time. All these parameters that stand in front of the differentials, what they tell us, that if I take dE to dV, I will get minus P. Right? So minus U total to dV, this is the energy that contributes to due to the attractions, divided by dV, it is minus the pressure that it adds to the system. Right? I put a minus over here, so this is P attraction. So, sorry? You remember this equation? Okay. So this equation tells us that if you take a derivative of the energy with respect to one of, this is ds, one of the extensive variables, you get something. Okay. Okay. So the P attraction, it is, we get N squared divided by V squared A. Where's the minus?
First minus comes from the V.
So there is minus over here.
No, it says you have two minuses. One from the dE over the V and one from the minus that you already have.
Additional minus. The one minus
So you get another minus, right? This is what you're telling me. Okay? Great. So what we have, we have P ideal, it is P plus P attraction. Okay? So remember, V, it is V free minus NB. P, it is P ideal. P ideal plus P attraction. Okay? So, we plug in inside the ideal gas equation, and what we get? We get P, we're using the P ideal, minus this guy, so minus A N squared divided by V squared. This is the pressure. Wait. So I'm using, this is the P ideal that I measure. Okay? And here I have the volume. What is the volume? The volume V free, okay, minus VV. So this is V. I'm not using V free anymore because I don't care. Minus NB. This is the substitution that I do. Right? I understand, but I'm using not this P. I'm saying the pressure, what is the pressure? Is P ideal minus P attraction. Minus P attraction have a minus sign. So I have plus, right? So I have minus. So you're saying this is plus. Okay, fine. Okay, so P plus A n squared divided by V, V minus NB equals to what? N K Boltzmann T. This is the van der Waals equation. Very simple arguments. You look on the volume, it's decreased. You have interactions with the matter, the pressure, it's a little bit, you have additional term over here. That's it, right? Okay. Now that we have this, we can do the same thing as we have done, with the ideal gas equation. We plot isotherms. So we will have volume as a function of pressure. Okay, why? Because we have pressure as a function of volume. Okay, why? And we need that dP to dV is more than 0. Okay, so we go to a very high temperature. We take out of this, so if you want to see what is P, right, so P equals to N K Boltzmann T divided by V minus N B minus A N squared V squared. Okay. So this is what you have. And you start to plot it. You want to use Wolfram or whatever. For high temperatures, it's boring, and it's simply decreasing function. Nothing interesting happens. You decrease the temperature, so this is setting a specific temperature over here, and looks what happens. So this is T1. Okay, we lower our temperature a little bit more. And we see that, well, some sort of a extremum starts to develop. But still, at any point on this plot, this condition is satisfied. Okay, so this is T2. T1 is larger than T2. And finally, we're getting to T3. What happens at T3? This is what starts to happen at T3. We get a minimum and a maximum. Well, get a minimum and a maximum, so what? But we know that in order for the system to reach equilibrium, dP is more than dV should be always satisfied. There is somewhere over here, we call forbidden land, okay? Or forbidden territory. So is the system, the pressure of the system indeed is going to increase with the volume? So no, something bad happens. You can say, oh, something bad happens. That means that the van der Waals equation is not good. It's broken. But it's a little bit more than that, right? Because we expect a jump, right? We expect that the system eventually, when you lower the temperature, at some point the system will become a liquid, right? So this forbidden territory, we can say, well, yes, there is a forbidden territory, but the only thing that we can take out of it, that there's some sort of a transition, right? There's going to be V alpha, and there's going to be V beta, and the system somehow, okay, somehow will transit from performing a jump from one volume to another. Right? Because this is what we see in nature. So the equation predicts by saying at some point this condition is not satisfied. The equation predicts that there is going to be an abrupt jump from one specific state to another specific state. How exactly it's going to happen? You need a microscopical theory. You don't really know what happens. You can say, well, I will somehow I will take this equation and I will try and understand what's happening in this region. It doesn't matter, okay? Because you say the system lives over here, okay? You increase the volume or you decrease the pressure a little bit, and then the system will go from one state abruptly to another. It doesn't live over here. There is no equilibrium states that the system for here or here or here or here. You can use this equation for something, but it already predicts there is a phase transition. The question is how exactly this phase transition is going to occur. Or the question that we can ask, given this equation, for given t, is there a phase transition? So this is easy. Well, the only thing that you say, well, there is a phase transition if this guy is not satisfied. So the moment that I have a minima or a maxima or maybe some other point, okay, or basically the moment that I have a slope that is positive, there is a phase transition. So this answer, to this question, we have an answer. But there are other questions. For a t where there a phase transition, what is the pressure and the volumes where this phase transition occurs? Okay, so I have some specific p tilde, I have v alpha, I have v beta. If indeed this equation predicts phase transition, what is p tilde, what is v alpha, what is v beta? So this question we still haven't have any answer. And the answer is how to do it. It's a technique called the Maxwell construction, and we'll develop it tomorrow. See you all tomorrow. Thank you.